Now, if you also want to find the probability, that will be n number of customers in the queue. So n could be any number. So what are chances that when I get to the hall or I get to the service point, there would be 10, 20, 40, 1, 2, 3, 1 million. N could be any number. Probability that there will be n number of persons or customers in the queue. And then we are saying that it is just the ratio of lambda over mu to the power n times the probability that nobody is in the queue, which is the same as probability, or so probability of n, or n number of people in the queue will just be p equals lambda over mu to the power n, so multiply by 1 minus what's it called, lambda over mu. Okay, so you just it's just that easy. So if I'm looking out for probability that there will be 20 people in the queue, then it's just going to be, if I know my average arrival rate and then my average service rate, it's just the arrival rate over the service rate to the power the number of people I'm expecting to be in the queue multiplied by probability that nobody's in the queue, and then that easy. Now, we also need to find, the other one is, if you want to find the average number of customers in the queuing system. Now, I want us to have a certain understanding of this. We are going to look at customers in the queue and then customers in the queuing system, or someone in the waiting line and then in the waiting system. Now, so let's distinguish between this. Now, when you say someone is in the system, it means that, so I put something in the bracket here which says that customers being served and in the waiting line. So here you are saying that you are waiting and being served. So let's just take a typical example of a banking scenario where you present your check to the bank official or the banker or the teller. She doesn't automatically give you your cash. Sometimes it takes some time. She will have to record and count the cash and on. Now all that time you spend some time waiting for her to count the cash, get authorization for your check, and then give you your money. So in that case, we are saying that you are waiting and being served. Are we okay? So you have presented your check to the lady at the counter. She's working on it. You're waiting to receive your money. If you take the case of a hospital, you could also find out that when you go to hospital, you can find people seated waiting at the consulting room, in front of the consulting room, and you can also have someone who is actually with the doctor being diagnosed and having conversation with the doctor. In that case, you are waiting and being served. So in that kind, we are saying that the customer is in the queuing system. Are we okay? So you can be in the waiting line but not in the system. And so for instance, if I present my check to the teller and she's counting the cash or getting authorization, I'm waiting right in front of her, there are other people who are not in my position but are just seated there waiting for me to be done, then it gets to their turn. Those people are not in the system. They are in the waiting line. So we say if you want to find the average number of customers in the queuing system, in other words, we say they are waiting and being served, then we say it is lambda over into bracket mu minus lambda. So, or the arrival rate over our service rate minus the arrival rate. Okay, and now we can also find the average number of people in the waiting line. So this is what I was saying. So for those in the waiting line, they are actually just seated. It's not yet their time. They are just seated waiting for whoever is with the teller to be done before they get. So we can also find those people in that instance. So the average number of people in the waiting line, we can say it's lambda squared over mu into bracket mu minus lambda. Okay, so the square of your average arrival rate over the service rate into bracket the service rate minus the arrival rate. Now, the other side, another set of things we can also find is, we can also find that the time it takes to be served. The average time a customer spends in the total queuing system. Okay, so these are four basic things that is very important to any organization. How many customers are waiting? how many customers on average are waiting and being served. Then how long does a customer wait when he or she is being served? And then how long does the customer actually wait seated, even before he or she gets the chance to be served? So when we talk of the average time a customer spends in the total queuing system, this is like waiting and being served. Is that okay? So that is when you have presented the check to the lady and you're waiting right in front of her counter and she's getting authorization for your check, or probably she is just counting your cash and you're waiting to receive it. Or probably if it's in the case of the hospital, then this is when you are with the doctor in the consulting room consulting with the doctor. But so here we say that it is your 1 over our service rate minus the arrival rate. So 1 over mu minus lambda. Then the other side is how long does the customer actually wait in total in the queue. So this is when the customer hasn't even gotten the chance to get into the system. So if you think about it, so for instance, if it's in the case of the hospital, how long do I wait sitting in front of the consulting room before the nurse comes to call me to come and see the doctor? Or how long do I sit waiting for my turn in the banking hall before I present my check to the the cashier? So it says that the average time a customer spends waiting in the queue to be served. So this is waiting to be served, and the previous instance is waiting and being served. Okay, so for waiting to be served, it is the lambda over mu minus lambda. You see, they share some funny similarities. The number of customers in the queuing system, and then the number of customers in the queue, and then the number of the average time waiting in the queuing system and the average time waiting in the queue. They kind of share very similar characteristics. You see it, and the denominators look just the same. It's only the numerators that kind of look slightly different, but very easy for you to just have this at your fingertips, and you can do lots of magic with this, even in your own businesses and environments. Okay, and then there are also instances where, well, maybe you want to assess how busy your server has been, or how busy the lady, the cashier, or the doctor has been. So we say that we want to find something we call the utilization factor, or the probability that the server is busy. Okay, chances that the server is being used is just the arrival rate over the our arrival rate over our service rate, and then also the chances that the server will be idle. Okay, it's just 1 minus the utilization factor, or which is 1 minus lambda over mu. And we do remember that in the previous instance, when we started, we said that the probability that there's nobody in the queue, that is 1 minus lambda over mu. So of course, if your server is idle, it means that there's no customer for the server to serve, or there's no one in the banking hall for the cashier, so she's there seated waiting for a customer. And that is the same as the idle time. So there's this example that we can go through. It says we'll go through the 8 characteristics with lambda being equal to 20 and mu being equal to 26 and n equals 10. So assume that the average arrival rate is 20 per hour, and then it's also 20. The average service rate is 26 per hour. And so and then let's assume n is 10. And you go through the process and it makes so much. Now, we also want to look at another dimension of this instance, where we want to bring in a certain trade-off of cost in between this thing. And it's quite interesting. So let's say, assume the management, so having done the computation from the previous instance, and then the management thinks that, well, the waiting time is unacceptable. What do you think we can do to improve? So for instance, you check the number of customers waiting in the queue, and you think that, well, it's too long, and you want to improve on it. What are some of the options available to you? Well, we looked at 2 options, and we said there are 2 possibilities, although there could be other ones. We could add an employee to pack up purchases, and that will improve the service rate, or we could add a new checkout counter. What we are saying is, well, How about if we have only, well, we said we are looking at a single server window. So for instance, if you take a typical banking hall and it is just one server or one teller, when you present the check, she may have to get up and go present the check to her head teller for authorization or something, and she has to do a whole, probably do photocopies of the check or take your ID card and all that. All that goes into the service time, and so you see that it takes a longer time for a customer to be served, and that would cause a lot of people waiting more in the queue. So what can we do? We can look at another option by saying, how about all those subsidiary services, we get an additional employee to do that. So when you present the check, she's there. Once she's working on counting the cash and getting the online authorization, other employee can go and do the photocopies and do all that for. And so that is like adding another employee. Or you can open another branch. And when you open another branch, that reduces your arrival rate. So if you open another branch, maybe customers can go to the other branch. So in either case, we compute our WQ, which is WQ. By now, we should all know that that's the time it takes to wait in the queue. Not in the system, but in the queue. Now, so time saved and the monetary gain. So we'll just compute our WQ, and then we'll compare the current WQ to the previous one and see what the difference, and see whether we would have saved some time. And then in that order, and then we'll look at the monetary gain. Then we'll do the cost and benefit analysis and see whether it's worth doing or not. Okay, so the previous example, where our lambda is 20 and then the mu is 30. So we recompute our WQ and do our analysis. So we are saying that adding an employee would cost 150 per week. And then the shop avoids a loss of 75 Ghana cedi per week for each minute that average customer waiting time is reduced. So let's look at this. So if I find my new WQ, it gives me a time of 0.006 hours. So that's in hours. If I convert it to minutes, you just multiply that value by 60 and that gives you its equivalent in minutes. So from the previous example, when I gave that one, you should do the 8 characteristics. Your time saved, the first WQ would give you 7.692 and the second one is 4.002. So we are saving 3.69 minutes. Awesome. Now, the monetary gain will be how much we are saving by the number of minutes we have saved the customer from waiting. So we have 276. So if we have 276, if we introduce another worker, and we'll be paying the worker 150 cedis a week, and each week we'll be saving 276. So the difference between how much we are paying that worker and then how much we are saving or we are earning is 126.75. I think it's a good offer. I think it's something. Or we can look at the other case where we can decide to build another, let's say, we can build another outlet which will reduce the arrival rate. So in this case, then if we add a new checkout counter, then we will be avoiding 75 per week, and each unit, for each minute that average customer waiting time is reduced. And then total cost is 6,000, which is the cost of 200 per week for the new cashier. Now the 6,000, we can consider that as the fixed cost because we may have to build a new facility and get all this kind of stuff. So we'll compute our new WQ, which is this, and then we have 0.0240 in hours, but if you convert it to minutes, it's 1.44 minutes. So the time saved is the previous WQ and this current one, and then we now have 6.252 minutes. Now the monetary gain is we'll multiply the amount of time we have saved by how much we earn whenever we save a customer a minute from waiting. We have 468. So, and the net profit is 468 minus how much we are paying. Now the point is we are not considering the 6,000 cedis, which is the fixed cost, because we'll consider it as a sunk cost. Well, it's not part of the operational expenditure now, so it's a sunk cost sort of. So here we are saving 268. So if we compare the two instances, we getting an additional employee and then building a new startup window. Where the previous case we are saving 126 and here we are saving 268. because it's a profitability, and when it comes to profitability, it's maximization. You would want to consider the one with the higher option. And so alternative 1 would give us an income of 126.75. Alternative 2 would give us an income of 268.90 per week. And so there's a difference of one. So I think the best is to pick option 2, which gives us the higher payoff. Okay, so all we've done, so just a little recap. So I'll take you back to the first instance. So this was the first question. Average arrival rate is 20 per hour. Average service rate is 26 per hour. Just go through the same processes, find the WQ, the WS, LQ, and all those kind of stuff, and just take note. And then we just add up a little something, some extra information, just to compare the two. And then, so all we just need to do is compute. All you just need to understand is when we are adding an additional employee, our service rate is going to improve. So we would say service rate will reduce by half. But when we are building another we're building another outlet, then this time around arrival rate would reduce by half, because if we had 10 customers who all would come to 1 point, if we now have 2 points, we can have 5 coming here and then the other 5 going to the other side. That's just the basic difference. You compute your R2, you find the difference between the new WQ, or the new time spent waiting in the queue, and compare it to the old one. The difference is whether we have saved or not, and then you just do this basic computation. Okay, and so we compare the two alternatives, and then we pick the one with the higher gains. I hope this session was fruitful, and I'll see you in subsequent sessions. Thank you.